Hello, I'm Karush. Today I'll be talking about off-policy evolutionary reinforcement learning with maximum mutations. This is joint work at University of Toronto and Borealis AI. Scaling up reinforcement learning has been challenging from three different perspectives. Large state spaces hinder the agent to understand complex world dynamics. These are often proprioceptive states or image observations. Large action spaces slow down learning by forcing the agent to choose from a variety of different action choices. These often result in sample inefficient behavior. Thirdly, excessive budget for training large-scale RL agents hinders development. The paradigm of trial and error requires many interactions and hence significant computational expense to master a particular task. Evolutionary methods, on the other hand, are a general class of genetic optimization algorithms. These methods utilize a heuristic search in the parameter space to find optimal solutions. Evolutionary algorithms have demonstrated scalable performance towards large states and action spaces. This arises due to their simplicity as black box solvers. Evolutions can be carried out in a computationally efficient manner. By parallelizing search over multiple workers, evolutionary methods present low computational times. However, evolutionary methods are sensitive to their parameters. A small change in hyperparameters may lead to a large change in their performance. Recent advances in reinforcement learning have leveraged evolutionary computing for effective exploration and scalability. A common alternative for improving performance is to combine gradient-based updates with evolutionary methods. Since RL agents are robust to their hyperparameters and evolutionary methods are found scalable, evolutionary reinforcement learning must improve scalability and performance. However, recent work presents major challenges in this area. Evolutionary agents can be sample efficient and take a lot of time to learn meaningful behaviors. Agents can also be prone to sudden environmental changes, demonstrating sensitive policies. Lastly, computational efficiency of evolutionary agents can be further improved. So let's explore and verify the problems of evolutionary reinforcement learning agents in a small toy example setting. Consider the discrete cyclic MDP process, which consists of only three states, S0, S1, and S2. The agent starts in state S0 and has three possible action choices to either go left, go right, or stay. For each right action, the agent receives a positive 1 reward. For any other action, the agent receives a negative 1 reward and the episode terminates. Thus, the objective of the agent is to continuously move clockwise in a cyclic fashion. This small example would tell us which of the algorithms demonstrate fast and optimal policy search. As we see, evolution strategies converge faster when compared to gradient-based RL algorithms. Additionally, the population is parallelizable in the number of CPUs, indicating that ES is much more computationally efficient. However, the ES algorithm is extremely sensitive to its hyperparameters. How can we improve the evolutionary methods with RL agents to effectively address these limitations? We introduced the evolution-based soft actor critic, an algorithm that combines ES with SAC for improved equivalence and scalability comparable to evolution strategies. ESAC abstracts exploration from exploitation by exploring policies in the weight space using evolutions and exploiting gradient-based knowledge using the SAC framework. The framework makes use of soft winner selections and mutations. Actors of the population undergo genetic crossovers in hindsight, which leads to transfer of dominant skills from winners to next generation offsprings. We tune the mutation noise using a novel automatic tuning schedule. Let's look at this method in more detail. We begin by sampling random actors and evaluating them in the environment. Based on evaluation, we select top K winners using a soft winner selection strategy. The top K members with highest rewards are selected to pass to the next step. Following selection, we mutate the winners to produce a new actors using crossovers. Crossovers take place between winners and randomly sampled actors of the population. Following mutation, we reinsert these members into the population. To control additional random noise arising from excessive mutations, we automatically tune the mutation rate during training. Once our evolutionary population is ready, we train a mutated soft actor critic RL agent using policy gradient method. The agent is inserted into the population and undergoes evolutionary training. A key component of our work is the automatic mutation tuning. Noise arising from mutation operations may compound over the course of training and result in degradation of performance. We control this excessive noise by starting off with a low mutation rate and gradually increasing it. Increments are based on the gap between best and average actors in the population. We use a smooth L1 Huber loss to keep the magnitude of updates small. However, the gap between best and average learners can be high in the case of large population sizes. To account for this, we use clipped versions of our updates. These restrict the magnitude to be constrained within a small region. Our evolution-based framework is competitive to modern-day RL methods. We compare ESAC to various RL and evolutionary baselines on a range of challenging robot locomotion tasks. The method combines the strengths of both evolutionary and gradient-based reinforcement learning methods to provide improved performance on various domains. Additionally, the method extends towards high-dimensional tasks such as humanoid. In terms of computational efficiency, evolutionary operations provide parallelization in the number of CPU resources. With increasing number of worker threads, computational time is reduced through a minimum, often providing 1.5 to 2 times speed improvement over reinforcement learning agents. The speedup allows us to incorporate more number of actors in our evolutionary population. Finally, we look at some of the qualitative behaviors acquired by agents in the environment. Evolutionary agents enable control of rigid body movements in high dimensions. For example, the agent can control a 21 degree of freedom humanoid robot within a matter of minutes. Policies produced by evolutionary RL agents are found to be robust as well. When placed at a steep angle, the walker robot can regain its balance and maintain a walking gait. These examples highlight the strengths of combining evolutionary methods with reinforcement learning agents. Check out our project webpage to know more about our work. Thank you.